Hello there. My name is Robert and I'm from northeastern Massachusetts. I'm currently in the process of upgrading my astrophotography system and thought it would be fun to put together a series of videos detailing how I went about choosing, setting up, and operating the new system step by step. Before I do, I wanted to introduce you to my current camera telescope combination, which is the Stellarvue C11 Schmidt-Cassegrain reflector. It actually started life about 20 years ago as a fork-mounted Ultima 11 unit, but since then I've removed it from its fork, added some cooling fans and internal flocking, and finally remounted it on this Lasmandi G11 German equatorial mount. The optical train is composed of a Celestron off-axis guiding prism equipped with an ASI174mm mini guide camera. For a main imaging camera, I'm using the same sensor, an ASI174mm monochrome camera, coupled to a ZWO 7-position electronic filter wheel and the Celestron f6.3 focal reducer. My filter wheel is a 2-inch, accepts 2-inch filters, of which only 4 positions are used. I'm equipped with a Bader luminance filter and red, green, and blue Bader 100 nanometer bandwidth filters. This setup has been really great over the years, and I've been able to capture some really nice high-resolution photographs of the moon, such as this picture of the crater Copernicus, and some limited number of deep sky objects, such as this planetary nebula M27, the Dumbbell Nebula. But what's been frustrating is the inability to really capture nice large objects such as the Andromeda Galaxy or the Rosette Nebula in a single field of view without having to put together a mosaic. I started by putting together a list of requirements for the new system. First and foremost was the ability to image a much wider field of view without serious vignetting, coma, or distortion of star shapes at the edges of the field. I also wanted an imaging speed faster than my current f6.3 focal ratio. My current ASI-174 camera generates quite a bit of noise, and the thought was that it would be a good time to go to a cooled camera system to bring those noise levels down. I also wanted something lighter in weight than my reflector, both for ease of mounting at night, as well as better tracking by not loading up my Lasmandi G11 mount to its weight limit. I wanted the telescope to have a reasonable cost, and I also wanted to add narrowband imaging capability by putting hydrogen alpha, oxygen 3, and sulfur 2 filters into my remaining 3 filter spots in my electronic filter wheel. And finally, it would be great if I could get some good support and service. So I went online and started having discussions with different people on what their experiences were with refractors that they were using. And I had gotten a lot of feedback to contact the folks at Stellarvue who were in California. I did, and I can't say enough about this company. They spent a lot of time walking me through what I wanted to accomplish with my astrophotography goals and what systems were out there, not just the Stellarvue systems, but competitive systems as well. So after a whole lot of consideration and discussion, as well as a lot of second guessing, I decided a good choice of telescope might be the Stellarvue SVX-130T refractor, equipped with a 3.5-inch feather touch focuser from Starlight Instruments. This unit is an apochromatic triplet refractor, meaning its lenses are arranged in 3 distinct groups, and that all incoming light, regardless of color, will converge on the same focal plane, minimizing chromatic aberration. Its light gathering ability is excellent for a refractor with a 133mm aperture. It has a focal length of 910 millimeters, giving it a focal ratio of f7, which met the speed requirements that I was looking for. And it has a whopping 60mm image circle. Now, modifying this with a 0.72x focal reducer brings the focal length down to 655 millimeters, but speeds up the telescope to a very fast f5 focal ratio. Even at this focal ratio, the image circle is still 42 millimeters, which is very large. And finally, the weight of this unit was under 20 pounds, giving me a net savings of about 5 pounds over my current setup. Since this telescope has such a large image circle, it seemed natural to look at full-frame cameras. ZWO makes the ASI6200mm monochrome camera, which uses a Sony IMX455 CMOS sensor. Having a full frame, it offers a diagonal of 43 millimeters, and with a 3.76 micron pixel size, this equates to a whopping 62 megapixel image size. The ADC of this camera is true 16-bit, giving it a dynamic range of 14 stops. The quantum efficiency is very high at 91% peak. And there's no danger of saturating stars under long exposure conditions since the full well capacity is over 51,000 electrons. I wanted a camera with low read noise, and the read noise is truly impressive at gain of about 100 for this camera at 1.2 electrons. This is the result of the cooling system, which uses a Peltier cooler to bring the camera to 35 degrees C below ambient temperature. One concern I have with such a large file size is the ability to transfer to my computer while imaging, but this camera also comes with a 256 megabyte buffer. So with this camera in mind, it would be great to see how it actually would combine with the telescope before actually purchasing it. And for this, there is a website that is really very useful. Astronomy Tools is a free website that has a number of different calculators and simulators, one of which being a field of view calculator. This is really useful for identifying what field of view we can expect from certain camera-telescope combinations. So in clicking on it, you see that the simulator will run either in a visual mode, binocular mode, or imaging mode. Since we're imaging, we'll click on this, and now we can put in the desired object for the simulation. Since I'm interested in a very large image such as Andromeda, we can just pull M31 from the list and go off to the parameters for telescope and camera. So looking at my existing system, we can actually go to a pull down and find the Celestron C11. Here it is. And it automatically inputs the focal length and the aperture. Since I normally run this with a 0.63 focal reducer, that can also be entered in. And my current camera is an ASI 174mm, which can be found here under ZWO 174mm. Once all that data is inputted, we can say add to view. And you can see the field of view for my current camera system, which is accurate. All I can really make out is the absolute center of the galaxy. So to compare that with the new camera system, we go back to here and find the Stellarvue. Here we go, Stellarvue SVX-130T. The focal reducer on this is 0.73. And the camera of interest is the ASI6200mm Pro. And once again, we can add to view. And now we see both side by side. And you can see that this choice of camera and telescope gives us a field of view that encompasses the entire Andromeda galaxy. The red inner frame is what I'm getting today for my current C11 system. Now, to go back and see what this looks like without a focal reducer and instead with just the field flattener, you can say none. And once again, add to view, and you can see the zoomed in frame that you would expect by removing the focal reducer. One final consideration in looking at the suitability of a particular telescope and camera combination is that of sampling. So we would like our image to be neither over nor undersampled. What I mean by that is in an undersampled image, there are too few pixels to capture the resolving power of the telescope. And that leads to low resolution, blocky square stars. But you can go to the other extreme as well, in which case the image is oversampled. In that case, the light is spread out over many more pixels than necessary, and it leads to bloated stars and also to longer than needed image times. So once again, if we go back to Astronomy Tools, we find that there's a great way to estimate whether we're under or over sampling for a particular set of sky conditions. So if we go back to the calculators and go down to CCD suitability, there's a lot of discussions here on the Nyquist sampling theorem, which I'm not going to go into. But at the bottom, we have a CCD suitability calculator. So once again, if we put in our telescope, which is the Stellarvue SVX-130T, and assuming we're going to be using our 0.72 focal reducer and using our ASI 6200mm Pro camera, you can see that the indicator is moving into the middle of this green field. The calculated resolution is 1.18 arc seconds per pixel. And you can see for good scene conditions, which is 2 to 4 arc seconds full width half maximum of a star, we would like to be in a range of 0.67 to 2. So we're smack in the middle of that. It's neither under nor oversampled. If we take a look at the same setup under very good scene conditions, you can see we start moving up toward the yellow, toward an undersampling situation, but this is still fine for the wide field images that we're trying to capture. And honestly, the days that we have really good seeing here in New England are few and far between. Now, if we go instead back to our OK seeing, and now we remove our focal reducer and use just a field flattener, you can see that we've dropped a little bit. The resolution's dropped to 0.85, but we're still in that good range of seeing between 0.67 and 2 arc seconds per pixel. And in this case, if we improve the seeing conditions, you can see we're solidly in the green since we're still below the 1 arc seconds per pixel sampling limit. So from a sampling point of view, this combination of telescope and camera is ideal for the types of conditions that I would be encountering here in Massachusetts. With all of this information in hand, I decided to place the order for a Stellarvue SVX-130T telescope and the ZWO ASI6200mm camera. The build and delivery time on the Stellarvue was running around 4 to 5 months, whereas the 6200 came very quickly from OPT. While I'm waiting for the telescope, I decided to build a new imaging train from my existing hardware and this new camera. And that's all going to be outlined in my next video. Until then, clear skies.